Okay, so if you have like a mathematical representation of this system, then you can, you know, apply some technique called the Routh-Horowitz criteria. So it's a give a tabular form representation. Then you can check like if any poles are related, located in the right hand plane or in the imaginary axis. So as you already know, if the poles are located in the right hand plane or there are multiple poles in the imaginary axis, that is the multiplicity is more than one, then the system will be unstable. So in some sense you get the like whether the system will be stable or not, we can find from this Routh-Horowitz criteria. And also you discussed about the in the lecture video you have seen the relative stability. So we'll discuss some basic problems from this areas. Okay, so discuss this problem. So first one. So you see you have like an input is given. So xt is the input and the corresponding output for a given system represented. So from that, can you comment on the like whether the system is stable or unstable? So let me start the poll. Okay, so you can answer through a poll and then we'll discuss. Okay, so yeah. Okay, so maybe we shall discuss this. Okay, okay, yeah, okay. So let's discuss this question. Okay, so you are given one scenario where you are given for the system a input. So this is blue line is input. So as you can see, this is a bounded input, right? So its value is 10 around 0 to 1, and after that is 0. So it's a bounded input, and the output is also, as you can see, is decreasing. So a bounded output. So for a bounded input, the response is bounded. But this is only one scenario, right? So it can happen that you may find one bounded input for which the system may be unbounded, or it may also possible that for all bounded inputs the output will be bounded, but you cannot infer that from only one scenario, right? So it's only one scenario, so there is no enough data, so you cannot determine the stability. Okay, so C is the correct answer, right? So and next we move to another question. So you have a open loop transfer function and with unity negative feedback. So whether the closed loop system will be stable or not. So again the basic question. Okay, so you can answer through poll. Okay, so let's discuss this question. Again, very simple one. So you just apply the Routh-Horowitz criterion to verify the stability. So because it's already so it's a open loop transfer function, right? So first you have to find the closed loop, and you are given unity feedback. So basically the characteristic equation Okay, so the transfer function will be g by 1 plus gh, where g is the feed forward gain and h is the feedback gain, and you are given h equal to 1. So the characteristic equation you will get from this equating the denominator equal to 0. That means you just have to equate 1 plus gh equal to 0, and h is 1, so you have just 1 plus g, right? So which is simply 2s4 plus 5 s cube plus s square plus 2s plus 1, right? Then you just write the Haru's table. So you have highest degree is s4, and s3, s2, s1 and s0. So for s4 it is 2, this one 1 and 1, and for s3 it is 5, 2 and 0. So first okay, so before going that also you first check whether the coefficients are all of same sign. So here they are also of same sign, and if they are not, then you already know that the system will not be stable, because that is the necessary condition. Okay, so now let's complete this Haru's table. Okay, Raut-Haru's table. So we have first 5 minus 4 by 5, so it is 1 by 5, so we have 5, and then 5 this is simply 1. This just this technique, right? So I'm just writing. Then next one is this 2 by 5 minus 5 by 1 by 5, right? It is 23 minus 23, right? Minus 23 by 5 into 5. So and the last one is simply, because this is 0 1, so you see that there are two sign changes there. So the system is not stable, and so the feedback system is not stable, right? Okay, so then we move to next question. So you have a open loop transfer function, and then you have to find the range of the k for which a unit feedback system. So here unit feedback means negative feedback. Okay, so closed loop system is stable. Okay, this is question 3. Okay. So just try, then we'll discuss. Again, very basic question. Okay, so maybe we can discuss this. Okay, so again you are given okay, open loop transfer function. So you have to find the closed loop transfer function, which is 1 plus g h, but h is 1, so 1 plus g, so that means 1 plus k s plus 2 by s into s minus 1 s plus 3. So okay, so you have also g above, so I can just write g. So this denominator will cancel out, so this and the denominator of the g will cancel out, right? So you just have this in the denominator you just have, I'm directly writing. Okay, so we have s into s minus 1 into s plus 3 plus k into s plus 2. Okay, so this is the characteristic equation. You can just simply find this. Okay, just you add this one. Okay, yeah. Okay, so this is the characteristic equation, right? So we are just interested in the denominator of this equation, so we are not calculating everything. Okay, so this is just simply you just expand this. So you have s time s square minus 2s plus 2s minus 3 plus k s plus 2 to 0 sq plus 2s square plus k minus 3s plus 2k equal to 0. So you have this characteristic equation. Then you write the Routh-Horowitz table. You can just simple one. So you have 1 there and k minus 3, 2 and 2k. Okay, right? So then you have this element will be 2k minus 6 minus 2k, so it is minus 6. Okay, minus 6, this is 0 and this is just 2k, right? So you see that there is sign change, right? This sign change already there. So even if you make k negative and this is not, there is no sign change, already there is sign change and you cannot change this, right, with your choice of k, because it does not depend on k. This is minus 6 only, so you cannot design this. I mean, with just only this changing that value of k, you cannot make the system stable. Okay, so you see that what is complete range of k for which this system will be stable. So you see that there is no such k value for which the system can be made stable. Okay, so then we move to next question. Okay, so you have a Routh-Horowitz table for a 7th order system. So you have 7 poles there, and the row of 0 at the S3 row, you have a row of 0 and 2 sign changes below S4 row. So how many imaginary axis or j omega axis poles does this system have? Okay, so again very simple question. So you just apply whatever you will learn, then you can just know how many poles are there, right? So okay, so you can answer through the poll. Okay, okay, question is clear, I hope. If not, then you can also ask if anything regarding that question, or the solution is not clear. Okay, you can interrupt and ask.
Sir, what is JW axis?
Oh, this is imaginary axis. Okay, right. This is S plane. So in the S plane, this frequency in the frequency domain, you write is like this, right? Sigma plus j omega. So this is this imaginary axis, j omega axis, and this is the real axis, right? As in the complex plane you write. So this is the sigma
Yes.
axis. Okay. Okay, so let's discuss this. Okay, so you are given that a seventh order system, so you know that there can be seven pole, right? So and S3 row becomes 0. So you know that if some row becomes 0, and it will happen only in the odd number, right? So before that row, you know that you can have a auxiliary polynomial where these roots can be located, symmetrically about this imaginary axis, if you can recall from this lecture video. So here you have S3 row become 0. That means you have four roots that are symmetrically located, right, around this imaginary axis. And below this S4 row, given that you have two sign changes. And you know that this auxiliary equation, this is just a, what happened that you have a polynomial and you have some factorization. And if some row becomes 0, you have this auxiliary polynomial that is one factorization of this whole polynomial, right? So you can just independently think also below this S4 row. This is just the analysis of only this auxiliary polynomial. Is it clear? So that means if the sign changes happens below this S4 row, that means two sign changes. That means there should be two poles. Yeah, two poles in the right half planes, right? Because the sign change are associated with the right half plane. So for S4 row, below that there are two right half poles are there. Okay, so we don't know whether these right half poles are like this, or they can also happen like this also, or so on. Okay, so that means that for each pole, like in this auxiliary polynomial, they are symmetrically located around this imaginary axis. That means if there are two poles, then there should be another two poles like this also for this auxiliary polynomial, right? So and you know that this imaginary axis pole can only happen only when one row is 0. So what I mean that we have S7 to S4 there, and have S3, S2, S1, S0. So you have some element there, and you got the 0 row here. Okay, so that means that
all the rows 0, no?
No, has a row of zeros. Okay, means this row is 0. All elements in that row is 0.
Yes, in S3 row. Okay.
Is it clear?
Yes, sir. Yes,
Yeah.
sir.
So you have a row of zeros at the S3 row. Okay. So S3 row 0 means your auxiliary polynomial should be your what order? Fourth order, right? So whatever analysis you have after this fourth order row, it's valid for this auxiliary polynomial, right? Auxiliary equation or auxiliary polynomial. So you know that, and if any imaginary axis pole has to be happen there, it can only happen in this auxiliary polynomial, right? Whenever you have a row of zeros, you know that there is an auxiliary polynomial for which symmetrically located poles are associated, and you can also have imaginary axis poles only for that case only. So that means in this auxiliary polynomial of fourth order, after that whatever analysis happens, only that is valid for imaginary axis, right? If you first count the because it is given that after S4 there are two sign changes, that means you know that two unstable pole are there, that is in the right half plane, right? So that means you must have two left half poles also that are symmetrically located to that right half planes, right? So how many poles now we have counted? 4, right? 2 right half planes and 2 left half planes for this auxiliary poles. So how many poles then the imaginary axis can have?
4 poles.
No, imaginary axis only.
Imaginary.
Only in this axis. Okay, I think you misunderstood the question.
2.
No. Again, this
Can be one.
No, okay. Okay. First thing is that whenever these poles are there, they should be in pair, right? Unless this is on the real axis. Is it clear? So
Yes, sir.
yeah. So whenever you should have conjugate poles, right? So they should be in pair. If it is not in the real axis, then they should be in conjugate pair, because your system has real roots, right? Like sorry, coefficients are real. So your one imaginary pole cannot happen in your system, real life system, where the coefficients are real. Okay. Okay, so let's again discuss this. Okay, so I think there is some confusion. So up to this it is clear, right? This S3 row is 0. That means that your auxiliary polynomial should be of what order?
Fourth order.
Yeah, fourth order, right? Then this route table, whatever comes after this fourth row, so you know how to proceed. So you proceed from this fourth row, you take the derivative and then replace these zeros with that derivative coefficients, and then you just compute this route tables up to S0. Okay, so after this fourth row, whatever comes, so this is for what? This is for whole as seventh order polynomial you are doing that, but after this S4, whatever come, it is for this auxiliary polynomial also, because you have a fourth order auxiliary polynomial. Okay, this is S4, something coefficient are there, and you have S3 because this system is seventh order, right? So for this polynomial, this analysis holds, right? Is it clear? I mean, whenever you have an auxiliary polynomial, so you have an auxiliary polynomial of fourth order, right? So whatever comes after that, yeah, okay, so whatever comes after that, the analysis is actually valid for this auxiliary polynomial. Okay, so for this auxiliary polynomial, which is of fourth order, you already have given that two sign changes are there, right? So that means for this auxiliary polynomial of fourth order, there are two poles that are located in the right half plane. Okay, so we don't care whether they are located here or in the real axis or something, right? So that means if the two poles are there, you know that for this auxiliary polynomial, they has to be symmetrical. That means for these two right half poles, there should be equally placed left half poles that are symmetrically located with respect to this imaginary axis. That means if some poles there, two poles are there, then you should have two left hand side pole like this. Or if there is some real axis, then you should also have some real axis pole like this, right? So how many poles do you have for this auxiliary polynomial, which is of fourth order? You have 4 only, right? So 4 poles means you already have two right half plane poles and two left half plane poles. So there cannot be any poles that is located in the imaginary axis. Okay, so for this fourth order polynomial. Okay, now the question will be, because this system is seventh order, so there are also 3 poles are left, right, which we did not account for. But you know that even if there is possibility of imaginary axis pole, that can happen only in the auxiliary equation, right? It cannot happen before. Just go through this lecture video again, and the tutorial there is also. I think there is some doubt is there, right? So this auxiliary polynomial, only after this auxiliary polynomial, that can happen only when there is a row of 0. After that you have like this auxiliary equation is there. For this auxiliary equation, all the analysis are valid from this. Whenever this row of 0 happens before that, so this is always a even order polynomial, as you can notice here, S4, because these poles are symmetrically located, right? So pairwise. And for this, you know that this can give rise to poles which are like this type poles that are symmetrical located around the imaginary axis or on the imaginary axis. Now for this fourth order polynomial, you see that you have two right half plane poles, right? Because there are two sign changes after that. So that means there should be two symmetrically located left half poles, right? So you have total 4 number of poles, which is the S4 system. Only 4 poles are possible for this auxiliary polynomial because it is a S4 polynomial. So you have 4 roots that are 2 are located on the right half and 2 are located on the left half. So you cannot have any poles in the imaginary axis, right? Is it clear?
Yes,
Sir,
sir.
can we ask in Hindi?
Uh-huh.
Can we ask in Hindi?
I didn't understand what. Can you repeat?
Sir, can we ask questions in Hindi?
Oh, okay, yeah, yeah, you can ask. Yeah, yeah.
सर जब स्पेसिफाई कर दिया है कि S4 सिस्टम है और तो सिर्फ 4 ही पोल्स के लिए देखेंगे
हाँ
और S3 ऑर्डर 0 हो गया तो सिर्फ 4 पोल के लिए ही देखेंगे।
हाँ, तो हाँ वही है।
उसके नीचे 2 साइड चेंज हुआ है तो 2 राइट हाफ प्लेन में होगा और
हाँ हाँ
जो S4 प्लेन है और S3 0 हो गया तो इमेजिनरी एक्सिस के साथ होगा तो लेफ्ट हैंड में होगा।
हाँ हाँ, तो बेसिकली क्या है, तो you have you have a auxiliary polynomial. So okay, so if you remember what is that auxiliary polynomial is that, so if a row becomes 0 in the Routh-Hurwitz table, so it will always happen in the odd number row. Okay, odd number power row like this S3. So that means that you have a auxiliary polynomial. So for this auxiliary polynomial, the poles will be symmetrically located on around that imaginary axis. That means this type of quadratic pole, or that can also happen in the imaginary axis, because this possibility is only for this auxiliary polynomial. Okay, so in the question you are given that a row of 0 is happening in the S3 row, right? So that means up from S4, whatever this analysis come in the Routh-Hurwitz table, it is for this auxiliary polynomial. And if you want to find any imaginary axis pole, it can only happen in this auxiliary polynomial. So what you do, first count that how many right half planes are there, poles are there. So which basically you can simply compute by change of sign. So there are two sign changes. So there are two right half poles are there, and because this only can occur in like symmetry around this imaginary axis, so there should be two symmetrically located poles in the left half plane also. So that means there are total four poles you have already accounted for. So for this fourth order auxiliary polynomial, so there are no other roots, so there cannot be any imaginary axis pole, right? Is it clear, or still you have any doubt?
क्लियर सर।
Okay, so then we move to next question. Okay, again this same analysis. So you have a closed loop transfer function. So you have to count like how many right half, left half, and imaginary axis pole, right? So I think you can apply this and again do. So whatever I told you, so just do for this. Okay, this problem. So this is question 5. So I am again starting on Paul. So again you do this Routh-Hurwitz criterion. So you just do this Routh table, and definitely you will encounter like if you encounter a row of 0, then you can have imaginary axis poles, right? If you don't have any a row of 0, then there is no possibility that imaginary axis poles will happen. Okay, so the number of sign changes will give you indication of right half plane poles. And if a row of 0 is already happening, so you have like how many right half plane poles are there for this auxiliary equation, and you can symmetrically how many left hand poles will be there for this auxiliary equation, and the remaining will be the imaginary axis pole, right? Okay, so let's discuss this. Okay. Okay, so you are given a closed loop transfer function. So you have, this is the characteristic equation. Okay, so on which you want to test like how many poles are, how these poles are located around this imaginary axis, whether they are in the left half or the right half or on the imaginary axis. And you already noticed that there is these coefficients are not same, right? Of different signs, they are not of same sign. So you already know that there can be at least one uh, pole in the right half plane, right? Because the system, the necessary condition is violated there, that is you need all these coefficients to be of same sign. But here there are some sign changes, so you already know that there are actually some, right half poles are already, at least one will be there. Okay, so let's just uh, compute this Horowitz table. Okay, Routh Horowitz table. So we have S5, S4, S3, S2, S1, S0, and S5 we have 1, then 3, 2. Okay, so S4 you have -2, then -6, -4. Okay, so so just compute this table. So you have -2, the simple computation, plus 6 equal to 0. Okay, and yeah, you just can check this is also 0 because 2 2 this one. Okay, so you have a row of 0, right? In the S3 you have this row of 0. Okay, so that means there is an auxiliary polynomial, and this polynomial can be obtained from this above row, right? So the polynomial will be what? So you have a highest order is fourth order, and these coefficients are for S4, these are for S2, and this is S0. Okay, so your auxiliary polynomial will be what? Or you can write also this plus 3s square plus 2, right? Is it clear, this auxiliary polynomial? So what you do, you replace these zeros with the derivative of this auxiliary polynomial. Okay, so this is 4s plus the derivative of this auxiliary polynomial 6s. Okay, so you have 4 and 6. So, or also I can divide by positive number also. Okay, like I can divide by 2 and make them 2 3 also. Okay, so I'm not doing that. Okay, you can also do for computation, you can divide any row by any positive number. Okay, it will not change. So anyway, I'm just writing 4 for this and 6 for this. Okay, so again you compute this complete this table. Okay, so we 4 into -6, so you have this minus 2 6, right, plus 12 equal to -12 by 4, so we have -3 there. Okay, and this is 4 minus 4, right? And this -18 plus 24 6 by 3. So you know how to find this, right? So compute this. So I'm just 16, uh, 16 so sorry, -2 by 3, right? And this is -4. You know how to proceed like this. So I'm just computing that, nothing else. So you see that okay, so this auxiliary polynomial is there. Okay, for this auxiliary polynomial, so this is a fourth order auxiliary polynomial, and from that whatever analysis come, this is valid for only this auxiliary polynomial, right? So how many sign changes are happening after this auxiliary polynomial?
What?
Okay, so
One sign changes.
yeah, one sign changes already happened there, and okay, so it's a fourth order, right? Sorry, yeah, sorry, I have done one mistake there. Okay, I should have kept this sign. Okay, okay, sorry about that. So it will be -8 -12, right? Yes, okay, equal to 0, or -8 or 12 means it is a -4 or -6. Okay, this will be minus. Okay, I should not change this sign. Okay, okay, so I have made that mistake. Okay, I will just repeat this. This is the auxiliary polynomial, right? Here we have this. So you don't change this sign. Okay, that will actually complicate this thing. I actually wrote after this multiply -1 because you cannot change sign. Okay, because this is already what happened, because then I also have to make this positive. Okay, this S. Okay, so don't go to that. Okay, I made that because I made this positive. Keep this sign there. Don't change this sign. Okay, this, because this is same as this also, right? This equation, but that means that this is also same, but here we have considered positive sign, but here this negative sign, but we already keep this here above with the negative sign, so that means we should not change this sign. Okay, or if we change this sign, then also we change for all. Okay, so this is already negative there, so we should not change this sign. Okay, so just keep this in mind. So because this auxiliary polynomial is given with negative sign coefficient, right? So don't change sign. So this will be the auxiliary polynomial. So you have -8 12 or -4 16. Okay, so then you proceed that. Okay, so you have this, so there is no sign change. Okay, then you can see. Okay, so there is no sign change means there is no right up plane poles, right, for this auxiliary polynomial. Is it clear? Okay, you compute this table. Okay, is it clear till now?
Yes, sir.
Yeah, so yeah, what I did was some mistake, because I'm taking this auxiliary polynomial with the negative sign coefficient. Okay, I should keep that negative sign. I should not flip that sign. Okay, if I flip that sign, that means I should have also made this +2, +6 and +4 and then proceed. Again we will see that. Okay, one assignment will be just proceed with positive sign there. Okay, for this auxiliary polynomial, instead of this -2, do what? Take it 2, 6 and 4 and then proceed also. You will get with positive sign all this coefficient. Okay, you will not, because this in the Routh-Horwitz criteria, what happened, this sign matters, right? This numerical value doesn't matter, so you should have same sign. So if you proceed with positive sign, you will get all positive sign. If you proceed with negative sign, you will get all negative sign. Okay, so for this auxiliary polynomial only. Okay, so for this auxiliary polynomial, as you can see, there are no sign changes, so that means you cannot have right half plane poles for this auxiliary polynomial, right? So there is no poles like this or this right half plane poles for this auxiliary polynomial. So that means you cannot have also left half plane poles, right? Because they should occur in the symmetrically, right, around this imaginary axis. So where these poles are located now, then you have 4 poles, right? This auxiliary polynomial is, this is a fourth order polynomial. So you have four poles. So where this pole will be located? Can anyone answer? Okay, so you cannot have poles in this right half plane or the left half plane, but you have a fourth order polynomial. That means the pole should be located on the imaginary axis, right?
Well,
So you can also check, because this imaginary axis poles are checking them are very easy. Okay, so your auxiliary polynomial is what? This one, right? Okay, so 2s4 plus 6s square plus 4 equal to 0. Okay, you just take 2 common, so you have s4 plus 3 square plus 2 equal to 0. You can also write it like s4 plus 2 square plus s square plus 2 equal to 0, or s square plus 2 plus s square plus 2 equal to 0, or you have s square plus 1 into s square plus 2 equal to 0. So where these poles are located then? Right? So these are the poles from this, right? You can simply verify this, because s square plus 1 means s square equal to minus 1, right? So s square equal to plus minus 1, which is actually this imaginary. Is it clear? Is it clear till now? Or do you have doubt? You can ask, right?
Yes. Yes, sir.
Yeah, so you see that there are 4 imaginary axis poles are there, and you already know that there is one sign change in the first 2 rows, right, from s5 to s4, or that can also be seen from this sign change in this uh, polynomial, because there are some sign, the coefficient are not same sign, so at least one pole should be in the right half plane, right? So 1 is in the right half plane pole and 4 are in the imaginary axis, so you have a fifth order system. So you have 5 pole already accounted, like 1 in the right half and 4 in the imaginary axis. So there are no left half plane poles for this system. So you have right half plane poles, it is 1, left half 0, and the imaginary axis 4, right? Okay, so okay, so then we proceed to next question. Okay, again the similar type of question. So you have to find the left half, right half, and imaginary axis roots. Okay, again you can apply the similar technique. Okay, so try. Okay, so maybe okay. Okay, so we may discuss this. Okay. Okay, so again you just continue with this route table. So you have 6th order polynomial. So s5, 4, 3, 2, 1, 0. Okay. So s6 it is 1, 2, minus 1, minus 2. For s5 it is 2, and there is no s3 term, so 0, and this minus 2 and 0. Okay, then you compute this just complete this route table. Okay, so we have this is simply 2, this is minus 2 plus 2 0. Okay, this is minus 4 by 2, so you have minus 2, right? Then you have this is 0 and 0, so it is 0 and 2 minus 4 plus 4 0. Okay, so you can see a row of 0 in the S3. Okay, so that means there is a auxiliary polynomial from S4 to S0. The fourth order auxiliary polynomial is there. And what is this auxiliary polynomial? So from this you have 2S4 minus 2 S square, sorry, minus plus 0 S square minus 2, right, equal to 0. This is S4 coefficient, this is S square coefficient, and this is the S0 coefficient. Or you have 2S4 minus 2 equal to 0. Okay, and the derivative of this will be what? 8 S cube, this is 0, right? So that's 8. Okay, so 8 here and this is 0. Okay, and then for this again you see that this is 0 and this is minus 2, right? You just compute the next table. So you can take this 0 to be some small number, because this whole row is not 0, so that only one element in the first column is 0, so you take this epsilon, a small epsilon. Then you again compute this table. So you have this is what, minus 16 by epsilon, sorry, minus plus 16 by epsilon, and you have just minus 2. Okay, just complete this table. Okay, so then you analyze them for how many left hand, right hand and imaginary poles. So imaginary pole can only happen in this auxiliary equation, right, S4. Okay, so for first we analyze this auxiliary polynomial, that is from S4. So S4 means there are 4 poles are possible. Okay, and you can see that you take epsilon to be some positive number, small positive number. So this is positive, this epsilon, you are taking epsilon to be some positive number. Okay, so this is positive sign. This is the 16 by epsilon, both are positive numbers, so this is positive, and this is negative sign, right? So there is one sign change in this auxiliary polynomial. Okay, so that means for this fourth order auxiliary polynomial there will be one pole in the right up plane, right? So if there is one right up plane pole for this auxiliary polynomial, we know that for this auxiliary polynomial the poles should be symmetrically about this imaginary axis, right? So there should be one left hand pole also for this auxiliary polynomial. Okay, so for auxiliary polynomial we have n equal to 4. That means 4 poles should be there, out of which one is in the, okay, I am writing right hand side and left hand side, and this is imaginary axis pole. Okay, imaginary poles. Okay, first we compute for this n equal to 4, this auxiliary polynomial. So one is in the right hand plane, and because of this symmetrical located, one will be in the left hand plane. So how many poles will be there in the imaginary then?
2.
Yeah, so 2 poles will be in the imaginary axis, right? And you see that how many poles till now you have encountered? This is 4, right? This is a 6th order system. You have accounted 4 poles already. So before this auxiliary polynomial, is there any sign change?
One sign change, sir.
Yeah, one sign change only for this auxiliary polynomial, right, that we already accounted here, right?
Okay.
Before that I am saying, okay, from S4. Okay, so just remember, whenever this auxiliary polynomial happens, so it's happening in the 4th row, right, S4. So after that whatever analysis come, it is for only for this 4th order auxiliary polynomial. Okay, so what you already have accounted here, you 4 pole you have already accounted. So before that whatever happened is, it is for other poles that are not in the auxiliary poles. Okay, so this 2, so there is no sign change, right, up to even S4. Okay, so other two poles will be where then? So you have 4 poles you have accounted, right? So other 2 poles, so can anyone tell where these 2 poles will be located?
The left hand plane.
Yeah, in the left hand plane, right? So you have another 2 poles. So these poles will be in the left hand planes. They cannot be in the imaginary axis, because for that to happen, a row should be 0, and that we are already accounted this in the S4 auxiliary equation, right? For this auxiliary, only this in auxiliary equation the imaginary pole can happen. So there cannot be any imaginary poles before that. These 2 cannot be in the imaginary axis, the remaining 2. And because there is no sign change before this auxiliary poles, this equation, that row, before this 0 row, right, there is no sign change before that, so there cannot be any right hand side poles. So these 2 poles should be in the left hand plane, right? So then you just come out left hand plane poles. Okay, so left hand plane, how many? 3 are, right? This 1 plus 2, 3. Then right half you have 1. In imaginary axis you have 2, right? And you see the total number of 6 poles, right? So this is the answer, 3, 1, 2, right? Is it clear? Okay, so just to recollect what we are doing, you just write the Routh-Horowitz table. So whenever you want to find like imaginary axis poles, then you must have a row of 0, right? Only then only imaginary axis pole can happen. Okay, so you see that S3 row is 0, so your auxiliary polynomial, which is always a even order polynomial, which is just before it, so that is the S4. So you have a 4 poles in the auxiliary polynomial. So that is, you again proceed the Routh table with this auxiliary polynomial, you take the derivative of it and you continue. So whatever analysis come after this 4th row, where this auxiliary polynomial has started, this analysis is only for this auxiliary polynomial. Okay, this 4th order auxiliary polynomial. So this auxiliary polynomial means it is a 4th order. You just write this 6th order polynomial there. You write it as some product of 2 polynomials. So this is one 4th order polynomial and one is 2 second order polynomial, because 6th is the highest order. So this 4th order polynomial, which you just write in this form, for which this analysis follows. Okay, so for this only you can have imaginary axis pole even when there is a row of 0. Okay, for this auxiliary polynomial. So and you see, first analyze this auxiliary polynomial. So here from S4 up to end, you see that only one sign change has happened. Okay, in the end only this here. So that means only one pole of this auxiliary polynomial is in the right half plane. And you know that this auxiliary polynomial can happen in like symmetrically around this imaginary axis. So there should be one left hand pole also symmetrical located to this right hand pole. Okay, for this auxiliary polynomial. So there are 2 remaining poles for this auxiliary polynomial, and they must be on the imaginary axis, because you do not have right half. This right half and left half should be in the pair, right, in the symmetrically. So you should have 2 imaginary axis poles. So you already accounted for this auxiliary polynomial 4th order, 1 in the right half, 1 in the left half, and 2 imaginary. And before that, whatever this auxiliary polynomial, this analysis for remaining poles. Okay, these 2 poles. And you see that there is no sign change from S6 to S5 and S5 to S4. So that means there is no right half poles for this remaining 2 poles. Okay, out of these 2 remaining poles, there cannot be any right half poles. That means these 2 poles should be in the left hand plane, right? So out of 2, there are in right left hand plane, so there is no right half. And because you know that imaginary pole cannot happen, only imaginary pole can happen only in this auxiliary polynomial. So you have all these poles. Okay, so then just count how many poles are in the right half, left half, and imaginary. Okay, so we move to next question then. Okay, so you have a characteristic equation. So how many poles are there in the -1? Okay, with real part -1. Okay, so you will answer, then we will discuss. Okay, so we can discuss. Okay, so yeah. Okay, so we can discuss this. Okay, so one way to analyze will be like shifting that. Okay, so as you already know how to find this imaginary axis pole, right? So if you have a row of 0, then you know that after that whatever follows, if there is, it is possible that it can have imaginary axis pole. So if there is no sign change, then you know that for this auxiliary polynomial there will be no right half plane poles. And similarly, left half plane poles cannot also happen for that, because they should be symmetrically located in the imaginary axis. So all poles will be imaginary pole, right, on the imaginary axis. So the question, if it is posed like that, how many poles are there on the imaginary axis, then you can simply apply this Routh-Horowitz criteria, and you can just analyze it, right, to find how many imaginary axis poles are there. Okay, now the question is that you are given that how many poles are in the with real part -1. Okay, so just draw this picture, and so this is the S plane, so this is imaginary axis, right, j omega axis. So now this is -1. Okay, so if the real part is given 0, that means only imaginary poles, then you know how to compute them, right, how many imaginary axis poles are there. Now this question is posed with real part -1. So what you can do, you can find another transformation where this -1 axis, okay, this is transferred into 0 axis for that. Okay, let it be z plane sum. Okay, is it clear till now? Then for this z transform equation, if you analyze for this imaginary axis, they will correspond to the real part -1 in the S plane. Okay, so let's define what. So you want this -1 line to be 0 line there. Okay, so what you will do, you take z equal to s plus 1. So whenever s equal to -1, you see that z equal to 0. So this transformation s equal to z equal to s plus 1 will transform this axis on this -1 to this 0 axis, or j omega axis, 0 or real part axis. Okay, to the z plane. Is it clear? You can ask, okay, if it is not clear, because this is you need to understand this, then you can proceed. Is it clear? Okay, so what we are doing is that you know how to analyze this imaginary axis poles, right? So imaginary axis mean your real part should be 0, right, of that pole. But now you are asked with real part -1. Okay, so -1 means if you can change this coordinate from into new you can transform this plane to new plane where this -1 axis will be the corresponding imaginary axis or real part 0 axis. Then in this transform coordinate, that is the z here, if you just analyze this Routh-Horowitz criteria, then you can find it how many poles are located in the imaginary axis of this z transform plane. Okay, so that corresponds to the -1 line of this S plane. Okay, so this transformation will give, that means you have to substitute in place of S, So s equal to z minus 1. Okay, so in place of s you substitute z minus 1. So this polynomial will be, okay, I don't have space here, so I have to write. Okay, so you write this polynomial. So let's remove this. Okay, so with this s equal to z minus 1, so we have this polynomial in the z plane. This is 3 z minus 1 square plus 4 z minus 1 plus 2. Okay, so z minus 1 q will be what? So z minus 1 square will be z square minus 2z plus 1. Okay, so into z minus 1, so here zq minus 2z square plus z minus z square plus 2z plus, sorry, minus 1, so it is zq minus 3z square plus 3z minus 1. Okay, so this is first term is zq minus 3z square plus 3z minus 1. Okay, then second term is 3 times this, like z minus 1 square, so you have 3z square minus 6z plus 3, then we have 4z minus 4 plus 2. Okay, you just simplify them. So you have this polynomial I am writing here, so it is zq, so z square is 0, then we have 4 plus 3 7 minus 6, so 1, so with z, again we have 3 to 5. Yeah, so this is the equation, right? So from that you can simply find z square plus 1 equal to 0. So the poles will be at what? One is at z equal to 0 plus minus j, and but you know that s equal to z minus 1, right? So that means s in the s domain the poles will be what? 0 minus 1 minus 1 and plus minus j minus 1, it's minus 1 plus minus j. So you say that 3 poles are located with the real part minus 1. Okay. Okay. So
Sir, if we directly solve the equation,
yeah, you can solve this. Okay, it's not a problem. Yeah.
yes.
Yeah, it's because the third order you can solve. Okay, if it is higher order, then it will be difficult, right?
Yes, sir.
Yeah, for like higher order, then you have to do like this. Okay. Yeah, it's fine. Okay, so the next question is, so you are given one closed loop system. Okay, so you have to find the relation between k and p. Okay, you can see this side. Yeah, let's do this. Okay, s plus 1 into s plus p there in the denominator. Okay, so you have to find the relation between k and p so that the system will be stable. Again, you just apply this Routh-Horowitz criteria and find the relation. So again, very simple question. Okay, so question 8. Yeah, so you can answer. So okay, so we can discuss. So this is again very simple question. So you first find the closed loop transfer function, right? So you analyze the characteristic equation or the denominator of the closed loop transfer function. So for this the closed loop transfer function, so first we find the g, that is the feed forward gain, which is these two transfer functions should be multiplied, that is k by s times this. Okay, so you have s times s plus 1 to s plus p, which is again s square. Okay, so s into s square plus 1 plus p s times p plus p, so you have equal to k by s q plus 1 plus p s square plus ps, right? Okay, so do I have space? Yeah, I have space. Okay, so I can do that. Okay, anyway, the closed loop transfer function will be what? G by 1 plus g, because h is 1 here, and you need only this characteristic polynomial, so this will be just sq plus 1 plus p. You can, okay, we compute it, so it will be clear. So you have g, so instead of g we have k by this term, right? sq plus 1 plus p square plus ps divided by 1 plus k by this term in g plus p square plus ps. So you see that these two will cancel, only this term plus k will remain in the denominator. So that means in the denominator we have sq plus 1 plus p square plus ps plus k, right? So this is the characteristic polynomial. You solve for the root, so you write this Routh-Horowitz table for this. Okay, so here s3 sq plus 1 plus p square plus ps plus k equal to 0. So the Routh table will be 2 1 0 1 p 1 plus p and k, right? This is p plus p square minus k by 1 plus p, and this is k. So two condition will be k should be greater than 0, and this should be also p plus p square minus k by 1 plus p should be greater than 0. Okay, so that means k should be less than p plus p square. Okay, and also one condition you also need, I have not put, that is the 1 plus p should be also positive, right? Because then only these two term will be positive. Okay, so I think in the option I have not put, but that condition also you need, right? 1 plus p should be greater than 0. Then only if the numerator is positive and denominator is negative, then you see that this term will be negative, right? So because only this is asked, so you have only this condition is there, but you also need this condition, right? Because otherwise this will be positive by negative, so this is positive by negative, so it will again be negative even though the numerator is positive. So you need both denominator and numerator positive. Okay, so this option is what, this one, right? Okay, listen, yeah. Okay, so we move to next question then. Okay, so you have a system, so we have to find like kp and kd for which this system will be stable. Okay, question 9. Okay, so you can answer through a poll, and very simple question. Okay, so maybe we can discuss. Okay, so again you find this closed loop transfer function, and from that you find this characteristic polynomial. Okay, so for first we write the closed loop transfer function. So first we write the g here. G is again, this is 4 times kp plus kds by s square plus 2s, right? So again h is 1, so you have to find 1 plus g, right? G by 1 plus g, and from that you find this characteristic polynomial. So this is what? This is 4 kp plus kds by s square plus 2s by 1 plus 4 kp plus kds by s square plus 2s, so equal to 4 kp plus kds by s square plus 2s by s square plus 2s plus 4 kp plus kds by s square plus 2s. These two cancel, so this is the characteristic polynomial, which is s square plus 2 plus 2 kd, sorry 4 kd, 4 kd s plus 4 kp, right, equal to 0. So this is the characteristic polynomial. So you just you know, one way to just simply, because it's a second order, so you just need this coefficient to be positive. Okay, so that is 2 plus 4 kd should be greater than 0 and 4 kp should be greater than 0. So it means kp should be greater than 0 and kd should be greater than say minus half. Okay, so that same thing you can also find from this route table also. Okay, so you have a second order system, so s2 s1 s0, so you have 1, this is 2 plus 4 kd. Okay, so, sorry, kp, right, skip one term and write in last one. So this 1 and 4 kp. Okay, and this is 2 plus 4 kd and 0, so last will be 4 kp again. You just completed the route table. So that means this should be positive and this should be positive. This is exactly what you can also guess from this coefficients, right? Because it's very second, like second order system, and this coefficient need to be positive. You know, second order system, how to define this, right? So kp is positive and kd is greater than minus half. Also the same thing follows from the route table also. Okay, so kp positive, kd minus half. Okay, this one. Okay, so then we move to next question. So for this characteristic polynomial, so you are given some characteristic polynomial of third order. So find the value of k such that the polynomial will have root at this point, s equal to -2 plus minus j. Okay, so you can answer through poll. This question 10. Okay, so maybe we can discuss this. Okay, so again one approach will be like shifting that S plane, right? What we do did for like previous question, if you remember, this one question. Okay, with the real part -1, so in there, here now we want with -2. Okay, so we just shift this plane such that here we have shifted this imaginary -1 plane, this one -1 plane to 0, or the imaginary axis plane. This is 0 real part plane line. Here we will shift this for -2, right? So one approach will be this one, and second approach I will discuss after this. So first approach, you can see that in the S plane you need this, because you know how to find the like how many poles are there on the imaginary axis, right? So but in the S plane, this instead of this imaginary axis, which is real part is 0 there, right? This sigma is 0 there. Instead of that, you have now -2 there. Okay, -2 plus -j. So these poles are located in this -2 axis. You want to transform this into another plane that is called with z, where this -2 will correspond to this imaginary axis. So that means what you will do, you take z equal to s plus 2, right? Then -2 will become 0. If s is equal to -2, then it will become 0. So any value on this -2 axis will be transferred to this imaginary axis. That means s equal to z minus 2. Okay, z minus 2. So you rewrite this equation using z minus 2. Then you analyze the Routh-Horowitz criteria and see if any row can be made to 0. That will give you the k value, right? And if any row can be made 0, and if there is no sign change after that auxiliary polynomial. Okay, so this is one approach, and another approach will be okay, like you already given two poles, because it's a third order system. You can find the other pole also directly. Okay, so there is no issue with that pole. Okay, so I will discuss that first. I will complete this okay, Routh-Horowitz table and this first method. Okay, so first transform this equation. So we have s minus 2, okay, sorry, z minus, I am writing in z, and z minus 2 whole square. Okay, so it is what, z square minus 4z plus 4. So z minus 2 q will be what, this into z minus 2. So it will be multiplied z square minus 4z plus 4 into z minus 2. So equal to here zq minus 4z square plus 4z minus 2z square plus 8z minus 8, right? So it is equal to zq minus 6z square plus 12z minus 8. Okay, so instead of s3 we have zq minus 6z square plus 12z minus 8. Similarly 10 square, because z minus 2 square is this. So what I am doing is, instead of s I am putting z minus 2, right? Z minus 2q plus 10 z minus 2 square plus 29 z minus 2 plus k, and I am just rewriting this, like expanding all terms. Okay, so 10 times this, so plus 10 times this one, z minus 2 square, like this term. So I did z square minus 4z plus 4, so plus 29 z minus 2 plus k. Okay, so it is what, zq minus 6z square plus 12z minus 8 plus 10z square minus 40z plus 40 plus 29z minus 58 plus k, right? So simplifying this, it will give zq, this is 4z square, then we have what, 29, 40, okay, that's right, 29 plus 12 minus 40. Okay, so it is only z. Then we have 58, okay, minus 58 plus minus 8 plus 40, right? So it is 26. So k plus k minus 26. Okay, So this is your characteristic equation, right? So you just write this Routh-Horowitz table for this. So you have SQ, S square, S1 and S0. So it is first 1 and 1, and 4 is 4, and this k minus 26, 4 k minus 26, right? So you complete this. So you have 4 minus k plus 26. So it is k minus 30 minus k, 30 minus k by 4, 0, and this is k minus 26. So k should be greater than 26, and you see that from this, if the row has to be 0, it should be k equal to 30. So you see that the solution will be k equal to 30, and this condition is also satisfied, the last one. So there is no sign change. Also this is positive after this auxiliary polynomial, right? Because then S1 will be 0, 0, right? If I take k equal to 0, and this element will be k equal to 30, sorry, this will be 0. So that means you have a second order auxiliary polynomial, and after that there is no sign change, right? For that is also satisfied, because k is greater than 26, because k is 30, so it is greater than 26. So you find this k is equal to 30. Okay. So another approach, okay, I will remove okay. So another approach will be what? Okay. So you are given two poles, okay, at this one, -2 plus minus j, and if you remember, for polynomials, nth order polynomial, what happens? This is summation of all poles equal to n. If there are n number of poles are there, because it is order is n minus 1 plus summation of I equal to 1, j equal to 1, n pi pj. You take two poles at a time, s minus 2, then minus plus continue minus 1 to the power n, then you take all the poles and multiply them. So you have pi I equal to 1 to n. This is constant term, okay. This is equal to 0. This is also this form of this characteristic equation where these poles are at the pi, okay. So for second order, you already know that this. So s square minus this will be summation of two poles, okay. One pole I equal to 1 to 2, two poles s, plus you know that these are p1 p2 multiply, right? Second order, when you multiply these terms, okay. So I will take minus there, s minus p1, s minus p2. What will happen? This is s square minus p1 plus p2 s plus p1 plus p2, like this. So this form you can see this, and this is the generalization of for nth order equation, okay. Is it clear? This one for nth order, this will be the form. If you take these poles like this, s minus pi, okay. So n number of poles, and we multiply them, p1 s minus p2 s minus pn, where poles are located this, then you can write this in also like this. So what that means, that this term will contain the summation of poles, right? Negative sign with summation of poles is the second highest power. Here this one 10 square, yeah. So 10 square, right? So this will be the summation of all the poles with negative signs, okay. So two poles already you are given like this, okay. So I will again clear this, okay. So then let other poles be located at some minus a, okay. Okay, so a could be positive or negative, okay. It cannot be imaginary, right? One pole cannot be in the imaginary axis, right? It can also be 0, not it's also possible, like only 0, like in the origin pole, but it cannot have imaginary part like this. Why? Can anyone answer? Third pole. Okay, third pole, can it be like imaginary? Can anyone answer why it cannot be? because you know that this imaginary pole should be in pair, right? Like this here, -2 plus minus j. Okay, so what I am asking, that you are given two poles, right? Already you are given that you want these two poles to be at this -2 plus minus j. So this third pole, let it be some pole I am assuming of this form minus a. It is located at a. Okay, the third pole. Yes. Third pole is located at a. So why I am not assuming this form like some JB? I'm just asking why I am not assuming of this form, because you know.
Sir, because it should occur in conjugate
Yeah,
pairs.
yeah, it should
Already
be.
we have.
It should occur conjugate pair, but we have only one pole left, right? So
Yes, sir.
yeah, so it can be only of this form, real part. So it can also happen in the origin also, right? It's no problem. It can happen origin positive or negative, but only in the real axis it can happen. Okay, so I am assuming third pole to be at A. So then you have this form, right? S minus 2 plus j. You can write like this also, 3 poles, right? In the product form. So you know this first term will be what? Negative of this pole summation. So that means minus of a plus, okay, -2, okay, plus j minus 2 minus j. This will be multiplied with what? A square term. So you have minus of a minus 4 a square, right? So which is actually what? 10 a square, right? Here. So that means a should be what? 6, right? Is it clear? -6, right? Sorry. Just compute this. This is what? Minus a plus. Sorry, I made a mistake. Sorry. Yeah. Okay, let me write it again. I have made one mistake. Okay, so what happens? This pole, we take the summation with the negative sign, right? So here this will be what? Summation will be -2 plus -2 4, right? And a this is right. Okay, so minus of a plus these two pole summation. Okay, so these are the -2. Okay, is equal to -10. Okay, it's negative of this. Okay, because this is 10 plus 10 is there, so I should have written -10, right? So a equal to 6, right? Minus negative part means it is located at the -6 hole. Okay, so if it is -6, then you know the last term will be what? This term will be multiplication of all three poles, right? So it will be 6 multiplied with other two poles, -2 plus j -2 minus j, and this is 6 times this is, you can see that it is 2 square 4 plus 1, so it is 6 times 5 equal to 30, right? So this case should be 30. You can also compute from that. Okay, so whatever you prefer, so it's just some like convoluted way. So the Routh-Horowitz table is a direct way. Okay, it is a little bit convoluted because you have to compare this with proper sign. Okay, but you can also use that. Okay, so we'll move to next question then. Okay, so you have a characteristic equation. So what value of k? So again you have a complex conjugate roots with real part -1. Okay, so again you can apply Routh-Horowitz, or you can just compare this coefficient and find. Okay, so maybe we can discuss this. So again, we have like a pair of complex conjugate roots with real part -1. So let this pole be like this. Real part is -1 is given. So I can assume some b, which I will determine with b in jb, right? So this is the two complex conjugate poles. Okay, let third pole be located at -a. Okay, so then from this characteristic polynomial, this is third order, so it will be s cube plus 6s square plus 13s plus k, right? So then you know that this is the negative of summation of all pole, right? So if you sum them, three poles, then with minus sign, then this will be this value, summation of all poles from this equation, right? This you can also apply Routh-Horowitz criteria. Okay, not problem. I'm just doing in this way. Okay, you can also like transform the Routh-Horowitz to like with 1. Okay, so you transfer to z. Okay, so okay, so summation of three poles will be what? -6 then. So that means a plus, the summation of this will be what? -2, right? So okay, -2 and plus minus jb will cancel, right? So it will be equal to 6. So you can find a to be what? -4, right? Okay, so I will like take this a. Okay, so a will be -4. So then k will be what? The product of all three poles, that will be -4 times, okay, minus, this will be plus sign because where is this? -1 to the power n. Okay, so minus will be plus, because -1 to the power 3 is -1. So here simply multiply this pole magnitude 4 into these two poles. So these are complex conjugate. So -1 plus j minus plus minus b will be what? Okay, so because okay, we cannot apply because we have not determined b. So anyway, we don't need that. Also, we can simply also put the root, because s we get -4, right? So this is the characteristic equation. So that means that it should also, -4 should also satisfy this equation. So what will happen if we put -4 there in place of s? Because -4 is a pole of this equation. So you know that if you put the value of the pole, the characteristic equation will become what?
0.
Yeah, 0. So for s equal to -4, this equation should be 0, right? So that means -4 to the power q, in place of s I am putting -4 plus 6 into -4 square plus 13 into -4 plus k should be 0. So from that also you can solve for k. So it is -64, it is 6 into 16, right? So 96, it is -13 into so 4 -52 plus k equal to 0. So we have the solving this, -64 plus 96 minus 52, so 20. So we have -20 plus k equal to 0 or k equal to 20. Okay, find the answer. Also you can apply this Routh-Horowitz criteria. So what you do, because you have 1 with -1 real part, so you transform this. So some z you take equal to s plus 1. So it will transform this -1 to imaginary axis in the z coordinate, and you write, instead of s, in place of s you can write z minus 1, and then rewrite this equation and do the Routh-Horowitz table assignment for solution. Okay, I don't know, I have no idea about that. I think you can ask in the discussion forum, because I don't know when this solution will be uploaded. Okay, you can ask in the discussion forum. Okay, so anyway, yeah, so you transform this into z coordinate with replacing s as z minus 1, and then rewrite this equation and this analyze this Routh-Horowitz criteria. From that also because you need on the minus 1 axis, that means that minus 1 axis in the S plane corresponding to the j omega axis in the Z plane, you look for rho of 0, and from that also you can find this k value. Okay, just try this and see whether you are getting the same result or not. Okay, okay, okay. So any doubt till now?